I will record actually.
Yeah.
Okay. So, few definitions, ore deposits and mineral resources. And then it can be, now my pointer doesn't work. Kidding me.
Have you turned it on?
Yeah, well, come on. And now, yes. Okay, looks like now it's working again. Okay, I see the point. Okay, so distribution of mineral resources. Mineral deposits are highly localized. That's a pile of good stuff, basically. They are neither uniform nor randomly distributed. Okay, you cannot draw a specific pattern for the distribution of reserves, resources on Earth. That is because concentrations of valuable elements are due to special, sometimes unique geochemical processes. And we will have a quick overview of that during this lecture. But first, we can have a look at what we call concentration factors. So basically, this is the amount of valuable elements we have to be concentrated in one place to be economically interesting to mine. Basically, what we do is to look at the composition of the average composition of Earth's crust here, and you have different metals and elements, and that's the concentration on Earth's crust in percentage. And then we know that we need these abundances to have a deposit economically interesting for mining. That's the amounts required for profitable mining operation. And then you can calculate the concentration factor. So the numbers are a bit old, but if you look at aluminium, you have 8% in Earth's crust. For an interesting deposit, you need 35%. That means the concentration factor of 4. Then we can go to elements like titanium, 0.57% in average in Earth's crust. But if we want to have a deposit that is economically interesting, we need between 32 to 60% of titanium in the deposit. So that's a concentration factor ranging from 56 to 105. But that is also highly dependent on the price of commodity. Okay, we are looking for very valuable elements to make a lot of profits, basically. Even if it's not very concentrated, we will look at the elements. Now, what we can do is to look at the actual abundance of chemical elements on Earth. In fact, this plot shows you the chemical elements of the solar system. They are sorted according to their atomic number. And here you have the abundance. In fact, it's normalized to the number of silicon atoms. What you have to understand from this plot, basically, most of the rock forming elements, the chemical elements we find in common minerals of common rocks on Earth, like a basalt or a granite. That's silicon, aluminum, sodium, magnesium, calcium, iron. They are quite abundant. But if you look at other elements we use in our economy, even abundantly, like chromium or nickel, copper, you see, they are already less abundant than these elements by a factor of about, that is 10,000 to 100,000. So they are not that abundant, in fact. And we can compare with other elements that are the so-called rare earth elements. These guys here. You know that the rare earth elements, for some of them, they are as abundant as copper. Not all of them, of course. But look at tungsten. It's almost as abundant as most of the rare earth elements, despite we use tungsten a lot. Lead as well is not that abundant. But then we look at very rare stuff, and that all these guys, basically, we have the platinum group elements, rhenium, osmium, iridium. They are less abundant by a factor of, I think that's 1 billion. So this stuff is really rare in the solar system and on Earth. And that's also the case for gold. So if we want to have enough concentrations of these elements in a deposit, we need to have process that basically concentrate these elements in one place. And that are the ore deposits or the mineral deposits. And then we have different types of mineral deposits. Basically, we have 4 main types. And the first one is igneous deposits. They are their formation is directly connected to a magmatic body. We have also the metamorphic metasomatic deposits. That's a huge family of different deposits. They are associated with a heat source. We will talk about that a bit later. We have also sedimentary deposits. They are basically formed through sedimentary processes, deposition of particles, or you have also deposits that are formed within sediments. And finally, we have mineral deposits that are formed at the surface of the planet, the very surface of the crust, and that's the supergene deposits. We will go through all these deposits during the lecture. But first, we can start with the igneous deposits. We can distinguish 3 types of igneous deposits. The first one is probably the most important in terms of volume and also in terms of what we can get in terms of elements. That's the pegmatite deposits. The pegmatite is a very, very peculiar rock. It's a rock made of basically giant crystals, giant minerals. We are talking about meter-sized minerals. And Because of the formation of pegmatites, we expect to find very weird minerals that contain elements that are not usually included in other minerals that form the rocks on Earth, the common rocks on Earth. So pegmatites, it's a coarse-grained igneous rock with interlocking crystals, usually found as irregular dikes. That means basically a big slab of volcanic rock or magmatic rock, cross-cutting all the other rocks and geological formations. We can find also pegmatites as lenses or veins, especially at the margins of big magmatic intrusions. That's batholith. And pegmatites are contain, as I said, many minerals like mica, tourmaline, beryl, and also lithium-bearing minerals. And some of these minerals are gemstones. The second main type of igneous deposit, they are layered ultra-basic intrusions. Basically, they are large magmatic bodies, but they are layered. You can see different units within the magmatic body, and that is formed by crystal settling in the magma chamber. The minerals, once they are formed, are heavier than the remaining liquid, and they sink into at the bottom of the magma chamber. So, and we can form layers of formed almost by one single type of mineral, and we can find minerals like chromite in this kind of deposits. Type localities of layered basic intrusions: Bushveld in South Africa, we will talk about it in a few minutes, and Isle of Rum in Scotland. To give you an example of layered ultra-basic intrusion, Bushveld is the place of several mining operations in South Africa. I forgot to show you this, this beauty. This is a spodumene. It's one single crystal. You see the size? 4.5 by 0.9 by 0.6 meters. This is the kind of mineral you can find in pegmatites. And spodumene is a pyroxene. It's a common mineral in lavas, in basalt, and it's a lithium pyroxene. Finally, the last type of igneous deposit, kimberlite diatrems. Diatrems are volcanic vents. They are funnel-shaped, and the kimberlites are a very rare type of magma, and we think they originate from the mantle. Kimberlites are gas-rich. They are ultra basic. That means they are enriched in magnesium and iron, and they go through the surface. And because they are gas rich, when they are close to the surface, you have a volcanic explosion, and that forms a diatrem. Kimberlites are very interesting because they contain diamonds. So let's look in details at pegmatite deposits. You have here a picture of a pegmatite that is a single feldspar. So we are talking about big crystals. And again, pegmatites are very peculiar because usually they form at the end of the crystallization of a magmatic body. So basically you have left everything that do not go into the common rock forming minerals. Okay. And that means you have a lot of weird minerals and a lot of metals that do not enter in the commonly found rock forming minerals. So I show you a quick example of a pegmatite deposit. That's the example of Pitika in Zimbabwe. It's actually a lithium tin cesium pegmatite. And this is basically on this sketch how it looks like in cross section. We have the country rock, the host rock here and here, and sandwiched in the country rock, you have a lot of different layers and subunits, if you want, and they are characterized by a specific type of mineral or a specific association of minerals. For example, here you have a layer of feldspar here. Then you have a layer which is beryl rich. Here you have a layer containing lepidolite. Lepidolite is a mineral that is that belongs to the clay family, and it's a lithium-bearing mineral. So that is really interesting if we want to mine to extract lithium. Then we have a zone here where we have quartz. Quartz is interesting if you want to make glass. And here our friend, the lithium pyroxene, spodumene. Where is it? Here. And here we have this lens made of petalite. This place is the best place for petalite. It's apparently you can find the best petalite in the world. And petalite is this kind of mineral, and it's also a lithium-bearing mineral. Okay. And finally, here we have a zone where we have spodumene and feldspar. If we go even more in details when we are looking at pegmatites, I give you just an example of lithium pegmatites. We can find up to 11 mineralogical and textural zones. So that's very complex magmatic body. It's a very complex geological object. And basically we see this, we have usually 5 zones. So this is a very simple sketch to show you what we can find. Basically we start from the center, the nucleus. Usually we have pure quartz. And in this area, we are talking about minerals, crystals that are several meters long. Then in this zone, we start crystallizing lithium mica lithium tourmaline, and beryl, which contains beryllium. And then we switch to the next zone, if you want, the inner zone. The main mineral association is quartz and feldspar. We can find also a bit of mica, but in terms of lithium-bearing minerals, we have also formation of lepidolite, and we have also tantalite, which is a niobium-bearing mineral. The next zone, the intermediate zone, is dominated by mica. We can find quartz and feldspar. The size of the minerals is much smaller, still 10 centimeters. That's pretty decent for a crystal. And we have spodumene, phosphates, and lepidolite in terms of minerals of economic interest. And finally, the last zone, named the marginal zone, we have tourmaline and mica, a bit of quartz, and feldspar. So pegmatites in general, they are complex body. We have a lot of weird mineralogical associations, and usually we find in this stuff a lot of interesting metals. Just a bit of, say, local geology, tourism or interest. The Ytterby mine, it's in the Stockholm archipelago, in the Vaxholm municipality, if I am correct. And in this place, we have been identified yttrium, that's terbium, erbium, and ytterbium. The last three are rare earth elements. So you have funny names for the streets. And you had a mine. Apparently it looked like that. And you can still find something like that. That's a feldspar, 15 by 7 by 5 centimeters. That's a nice feldspar. It's on my balcony. So the point is, it looks like that. I could just leave you read the sign on the mine, but I will just give you the basic info. Basically, the mine was operated for feldspar and quartz for the porcelain industry that's related to feldspar, and glass industry that is related to quartz. And many famous chemists, I would say they were in fact geochemists, like Renaus and also Gadolin, investigated the minerals from this place, and they discovered the elements I mentioned: yttrium, ytterbium, erbium, and terbium. Yeah, I have all of them. Okay. So if we look a bit in details, the rock look like that. I think this star pattern you see on the picture, that was made probably by explosives. But in a more close look, this is what you see, and you see there's black patches. They are gadolinite, full of rare earth elements. Okay, so just to remember, pegmatites, that's good stuff. Now we can switch to the next type of igneous deposit, and these are the layered igneous intrusions. As I said, they are formed by crystal settling, sinking of crystals at the bottom of the magma chamber, because the newly formed minerals are denser than the remaining liquid. That's something we see. It's a classic process in magmatic bodies. And usually we have formation of chromite layers. That's magnesium, aluminum, chromium oxide. We have formation of magnetite layers. That's an iron titanium oxide. And we have formation of iron sulfides. And among them, we have pyrotites, pentlandites, and pyrites. And they contain also nickel and platinum group elements. So that is interesting for, in particular, the PGEs. About type localities, I mentioned already Bushveld. You have the same kind of layered intrusion in Sudbury, also in Greenland, Skagerrak. You have to keep in mind, we are talking about huge magmatic bodies. And I will give you the example of the Bushveld intrusion. And this is where you can find it in South Africa. And you see the scale. I think that's kilometers, dozens of kilometers. That's super big. It's not continuous, but nevertheless, it's super big. As I said, you can find mining operations on this layered intrusion, because in fact, what you see in cross-section is that you have a succession of different rocks. They were formed by this process of minerals sinking into the magma chamber. So you start with something like an orthosite on the top, which is made out of feldspars. Feldspars are relatively light. And then we go into gabbro. You have feldspar, but you have also pyroxene and a bit of olivine. Feldspars, pyroxenes are heavier than feldspars. Olivine are heavier than feldspars and pyroxene. And you go deeper and you have something that is getting denser. You have a bit of complication. Here we have bronzite, which is made of pyroxene. Here we have another pyroxenite, a rock made basically of pyroxene. We are talking about more than 80%, a bit of olivine sometimes. But the black layers here are chromite layers. If we look again at a cross-section, a bit more simplified, this is what we see. We have different zones, and at some point, we have magnetite layers here again, and then we have what we call the critical zone, and this part of the Bushveld is very interesting because we have chromite layers, but it's very enriched in sulfides. We have a lot of PGs in this layer. That's the Mirensky Reef. So keep in mind, big intrusions, layered, and these layers are formed by sometimes one type of mineral. Oops. So that is the core process to form these layers. We have a magma chamber, which is cannot be close to the surface. It has to keep the heat, the initial heat. And basically the minerals start crystallizing and they sink and they form layers. One type of mineral crystallized according to the physical and chemical conditions. That means temperature and pressure. Minerals are specific to temperature and pressure, but also chemical composition. You change the chemical composition of the liquid, you change the type of mineral that is crystallizing. That's why you have layers of different composition. You can see that a little bit more in details on this sketch. We start forming olivine. They settle down at the bottom of the magma chamber. They are super dense because they contain a lot of iron, a lot of magnesium. Then we start crystallizing chromite, slightly less dense because you have more aluminum. And then you form a layer made by chromite only. The chemical composition of the liquid, of the remaining liquid, has changed between the formation of the olivine and the chromite. And then it keeps changing, and then we switch to another mineral that is plagioclase. And then you form a layer of plagioclase. And that is the top layer in the bushveld. That's anorthosite. Once.
I have a question. On the previous slides, you had like different chromites layers.
Yeah, I know.
So that's something that I don't get now.
Yes. Nature is very complex because you have formation of layers. Sometimes they can, how to put it simply? Well, the magma chamber, it's a mush. You have liquid, but you have also solid. So sometimes you have convection within the magma chamber. So basically you steer the stuff. And sometimes what happens is that you have, it works very well for plage. You form a layer of plage, but it's in the middle, more or less, of the magmatic body. It's floating within the liquid. And once it reaches a certain density, it sinks, press the liquid. And then the liquid that is pressed has a different composition. You have different processes. Magma chamber processes are complex. We know that some processes like what I told you, this convection within the chamber, you can have also re-injection of fresh magma into the chamber, something that has not underwent crystallization. The fresh batch goes into the chamber, start crystallizing, and you on the top of your layer of plage here, you start crystallizing another layer from this fresh batch of magma, and you start with the first mineral, olivine. So you can have a succession like that. Olivine, chromite, plage, olivine, chromite, plage, etc., etc. Plus complex processes. It crystallized on the wall of the magma chamber. It collapsed. So basically it's spread on the top of the previous layers. Fantastic. Magma chambers are fantastic. So back to the real thing. This is what you obtain. That's chromite, and I guess that is olivine. I can't really see, but that close to the screen. Okay, so more like for layered intrusions, more like a dynamic process compared to pegmatites, say. Okay. The last one, and we will have a short break. Kimberlite diatrams, as I said, they are basically funnel-shaped pipes. We believe that the kimberlite magma comes from deep within the crust or even in the mantle. It comes from very deep. It's full of gas. When it's close to the surface, it explodes and creates this kind of geological object. Within the diagram, you have a lot of material. You have fresh magma. You have also blocks from the country rock, but you have also stuff that the kimberlite magma brought back from the depths. And one of the things that it brings back to us is that's diamond. And diamond forms at depths, it needs pressure. And kimberlites are the only magma producing diamonds. And we find them only in diatrams. Okay. Question, yes.
Yeah. Are they actually producing the diamond when exploding, or is it more like the diamond comes up with the...
No, it must be very deep.
Okay.
Because once the explosion doesn't produce much pressure. So basically the explosion, the explosion releases the pressure. You don't create it. So the diamonds were produced in depths, very deep. Actually, we don't really know. We think about 200 kilometers deep, 150. So that's what we think.
What causes the color of the diamond?
I would say that's the impurities. So diamond is pure carbon, but you still have some elements, and I think that's what creates the color of the diamonds. Okay. Actually, it's longer than I expected. Actually, that's not my lecture, technically. So we are halfway. So you want 5 minutes break and we come back? Yeah. Okay. So we have a break. Any question on Zoom?
No questions. We'll follow.
Okay.
Fine. Thanks.
Salad in the refrigerator. Salad in the refrigerator. Well, pure salad, 200 grams salad. No stupid questions, but minerals and metals, are they interchangeable?
What you mean?
I think in the first slide, when you're about the definitions, I was trying to analyze what the difference between metals and minerals were, but I was thinking that, ore, mineral deposit, and it's kind of like varied where metal was and mineral was. So I was thinking, what's the difference between metals and minerals?
Well, metals, well, you can consider them as a chemical element that enters chemical elements that enter into a mineral. Okay. I will do it old school. I will do it old school. Yeah, just there in the small corner. two atoms. Okay, it's very simple. You have an object which is made by two different atoms with a well-identified
Structure. Or something.
exactly.
Yeah.
That's a mineral.
Yeah.
Atoms could be silicon, could be iron and titanium. Usually, most of the chemical elements on Earth, they form minerals. Some metals do not form, strictly speaking, minerals. We call them native, like silver, like mercury. You can find them as pure metal on Earth.
And pure metal, you mean 100%?
No, you have impurities. Come on, nature is not perfect.
No. I mean, I'm a bit novice in this.
Well, that forms through a geological process, whatever it is. That means it's not perfect. So
it was a good explanation. I think I finally made it. You know, you always see this metals and minerals. It says, you know, renew. It always says.
You didn't go to my course about minerals in our natural resource course.
No.
Mm-hmm. No, you didn't.
In the kimberlite, like you said, it's a gas-rich magma, which explodes. And does the crystallization happen fast enough that there's still gas inside? Or does all the gas?
It's a magma. That means it's a mixture of gas, solid, and liquid. At some point close to the surface, the gas is not dissolved anymore in the liquid. That makes the explosion.
That causes the explosion.
Yeah.
But does all the gas like dissolve and does it accumulate, or is there still some?
I guess
bubbles or impurities.
I guess once you are close to the surface, you have already some degassing. You have already some crystallization.
Yeah, but what is faster? No.
Depends.
Okay.
Depends how fast the magma is rising toward the surface. If you have a lot of, say, fracture in the country rock, it will go faster. But if the magma has to dissolve the country rock, digest it, it will take some time. Crystallization will happen.
Maybe a bit late, but you are recording soon.
Yeah.
Good.
Okay. I don't know if I can make it in half an hour. Okay. You ready? All right, let's start again. So you can see the slide on Zoom. Yeah.
Yep, fine.
Okay. So we start again. Now we switch to the second main type of mineral deposit, and that is the metamorphic, metasomatic mineral deposits. I would say that is a very big family of deposits. You have a lot of different things, a lot of different types of deposits. In fact, different processes that resulted different types of mineralizations, and that resulted in a complex classification. So we have different ways, different, how to say, we have, depending if we describe the mineralization, depending if we describe the formation process, we have a classification. Main classifications, I would say, 4 of them. Deposits classified according to the occurring mineralization. For example, you have a very famous type of deposit, that's iron oxide copper gold, because it's economically very interesting. You have, we will talk about that. We will talk also about porphyry copper deposits. So that different mineralization, different type, a different box to classify the deposit. Deposits classified according to the formation process. We will see that a little bit later. Deposits formed during metamorphic processes, opposed to deposits formed during hydrothermal activity. Well, usually when you have metamorphism, you might expect some hydrothermal activity. Sometimes distinguishing between 2 processes is very complex, very difficult. We can also classify the deposits according to the temperature formation. And we can also classify the deposits according to the geological setting, where we can find them in a, say, more or less systematic way. Subduction setting versus mid-ocean ridge setting. And we will see that in a moment. Within there's metamorphic, metasomatic deposits, we can distinguish 4 different, say, subtypes. We have disseminated mineral deposits, basically the economically interesting mineral is scattered within the host rock, but it's concentrated enough to be a worthwhile ore. We have also metasomatic mineral deposits. They are formed by the action of a fluid in the vicinity of a magma body. A large family of deposits as well. So I mentioned already the iron oxide copper gold deposits. We will talk also about apatite iron oxide ore, like in Kiruna. The third type, hydrothermal ore deposits. That's a mineral deposit that's precipitated from a hot aqueous solution that could be associated with a magmatic body or not. We have a lot of mineralizations associated with this kind of ore deposit. That could be that could also occur as veins. And finally, we have volcanogenic deposits. And the best example for this kind of deposits it's the volcanic massive sulfide deposits, or VMS. They are black smokers, and we will talk about that quickly. For three of these deposits, the metasomatic, hydrothermal, and volcanogenic, we have always fluids involved. Okay, you need to transfer the elements using the fluid. A bit more details about the disseminated mineral deposits. As I said, the ore mineral, the mineral of economic interest is scattered within the host rock. Typically, that's the case for the porphyry copper deposits. And here you have a sketch that shows you roughly how it forms, how it occurs. We have a magmatic body, and we have different zones around part of this magmatic body, and surrounding these zones, we have an area where we have transformation of the rocks, mostly by heat. And then this is where you form minerals of economic interest. And you can locally concentrate a few elements. It might look like that. You have a weird framework of mineralization. This is what it looks like in real rock. Could look also like that. You have veinlets of sulfides, and you have also nuggets of sulfides scattered within the rock. And this is what it looks like in another way. To illustrate that, you have a magma body, and you have different zones with different mineralizations, but you have basically an outer shell which contains scattered minerals that contain the elements of economic interest.
Looks like a tooth.
It does, indeed.
It could be giants.
Yeah.
Old giants, right? Very big giants, let's say.
Okay, let's switch to the next one. So metasomatic mineral deposits, minerals formed in the close vicinity of a magma body by chemical transformation of the country rock, but also the newly formed magmatic rock with the help of fluids. Basically, we are close to a magma body. You have a lot of heat, you have a lot of fluids, and you have a lot of chemical reactions. You transform the minerals, elements move, and then you form ore deposit. You can find three types of three shape types of this kind of deposit: inverted cup, hollow cylinder, and tabular or inverted bowl. In the inverted cup case, the formation of ore minerals happens in the host intrusion and the country rocks. Same thing for the hollow cylinder, but for the tabular or inverted bowl, it's only in the country rock. An example of this kind of deposit, it's iron oxide, copper gold deposit, and specifically apatite iron oxide ores. They are referred as the Kiruna type. We have a massive magnetite associated with apatite, which is a phosphate. And this phosphate is particularly rich in rare earth elements. These apatite iron oxide deposits are usually associated with subduction zones. So a lot of magmatism, a lot of fluids coming from the plate that is going into the mantle. But we can find also this kind of deposit in extensional settings like continental rifts and possibly mid-ocean ridges. They form lenses shaped or disc-like ore bodies. And they occur from the Paleoproterozoic. We are talking about 2,500 million years to 1,600 million years. And that is the case for the Kiruna deposit. But we have also quaternary deposits, and that is the case of El Laco in Argentina. Few more details about this kind of deposit. 355 deposits and prospects worldwide. They contain also low titanium magnetite as a main ore mineral, fluorine-rich apatite, and we have also hematite, which is also an iron oxide. Very big deposits, large sizes, high grades. For Kiruna, we are talking about reserves of more than 2 billion tons and an ore grade more than 60%. Finally, how they form. The origin is not fully understood. It's an ongoing debate. Two main lines of thought. Orthomagmatic formation, that means high temperature associated with a magmatic activity, or hydrothermal ore formation, low temperature. We are talking about something like up to maybe 400 degrees. But typically, I would say 200, associated with chemical transformation of the rocks. The Kiruna type is the dominant source of iron in Europe, and Sweden is the country with the dominant concentration of Kiruna type ore deposits in Europe. So that's good for Swedish economy, I guess. Now we can look at hydrothermal deposits. That's a mineral deposit that precipitates from a hot aqueous solution, as I said, with or without involvement of a magmatic body. We have a large range of mineralizations. And basically, this is how it works. You have a heat source, you have a lot of fractures, you have water coming from the rain, could be also water from, could be seawater, could be also groundwater. So the water circulates within the fractures, within the porosity, the pores of the rocks. And eventually you transform the rocks, you mobilize the chemical elements, and at some point you crystallize, you precipitate new minerals that concentrate different chemical elements. So that is two ways to represent that. It's more or less the same. What you have to keep in mind, fractures, fluid, and a heat source. Water circulates, carrying chemical elements, and at some point the solution precipitates and you form new minerals, and then you have ore deposits. Finally, volcanogenic deposits, as the name indicates, of a volcanic origin. And we have this kind of deposit formed in volcanogenic sediments that are formed from volcanic rocks. But the most important thing, the most important type of deposit for in terms of economic interest are volcanic massive sulfides, VMS. That's black smoker environment. All the big VMS deposits we have on Earth, we are quite sure they were formed by black smokers. How it works, we have a mid-ocean ridge. We have two tectonic plates that are splitting apart. And just beneath the ridge, we have a magma chamber producing a lot of magma. Because the two plates are pushing in different directions, you have a lot of fractures. This is what you see here. That means seawater goes into the oceanic crust, goes close to the magma chamber. Then you have a lot of reactions, a lot of chemical reactions. You form that eventually, but before you form this. This is black smoker. More in details, you have chimneys and you have plumes of hot water carrying a lot of chemical elements that were leached by the seawater from the rocks of the oceanic crust. In more details, this is what shows this sketch. You have seawater, it's cold, it's alkaline, it's sulfate rich, it's oxidizing, and contains very few chemical elements, metals, goes into the oceanic crust, goes close to the magma reservoir, and then it is transformed, it becomes very hot. So it has the capacity to leach metals, and it becomes an hydrothermal fluid. It's hot, it's acid, it's reducing, it's rich in sulfur, and contains a lot of metals. So this is what looks like a black smoker chimney. We have inside, we have sulfides, and as it goes toward the top, we have anhydrite, which is a sulfate. And here you have the plume of hot fluid coming out. In fact, the black smokers, the chimneys, have a life. They evolve through time. They start as small anhydrite cones, and then they evolve. They grow, formed by anhydrite and some sulfide. The sulfide are very localized at the bottom. And when they get quite mature, you have a lot of sulfides at the base, and then anhydrite is localized at the top. Eventually they collapse and they form a crust. And underneath, you have a lot of, you have a network of fractures, and you have a lot of fluid circulation. and you form sulfides. So that's the way you form most of the massive sulfides deposits on Earth. All the massive sulfide deposits that are exploited nowadays, we think they were formed like that. Okay. Okay, that's the third type of mineral deposits, that's sedimentary deposits. We can distinguish three of them. There's deposits result from the accumulation of or precipitation of a sediment. The first main type is iron banded formations. They are very old, in fact, because they formed at the time Earth's atmosphere was oxygen poor. And what happened is that when oxygen began to be released in the atmosphere, iron that was in solution in seawater combined with oxygen formed insoluble oxides that eventually precipitated with silica to form beds of red chert and iron ore. We have also placer deposits. They are concentration of erosion-resistant minerals or metals like gold, platinum, and diamonds. And there's native metals and minerals are transported by streams, groundwater, and they accumulate locally when the water does not have the energy to transport them anymore. We will look at that in a minute. Finally, we have a deep ocean precipitation of metals and minerals, and there's our manganese nodules. They are formed by the precipitation of on the deep ocean floor. These nodules are mixtures of different oxides, manganese oxides, iron oxides, hydro oxides, and we can find also small amounts of copper, cobalt, nickel, and zinc. These nodules grow like onion shaped objects. They form layers, concentric layers, and they precipitate directly from seawater. And usually we find them at the bottom of the large oceanic basin.
Just a quick control question for me in regard to metals and minerals. Gold is a metal.
Gold is a native metal. It doesn't combine with other elements to form a gold bearing mineral like silver.
So you can say that Val is off there with minerals such as gold.
It's recorded. Okay.
Excuse me, I have another question. You mentioned that these manganese nodules, they are like onions, you see, they are layered.
Yes.
Do the layers sort of different in composition, or are they generally the same?
I would say they are different in composition, but I would not bet a nice bottle of whiskey on it. I would expect so, but actually I don't know.
Okay. Thanks.
Okay. Finally, we have sedimentary exhalative deposits, SEDEX. They are very important as well in terms of recovering valuable elements. They are zinc-lead deposits, and they are formed by discharge of metal-bearing fluids. In fact, salty waters or brines, and they discharge these metals usually as sulfides in marine sediments, and they form massive sulfide lenses. And this kind of deposit is usually very good for a profitable mining operation. Just a quick word about the placer deposits. As I said, density contrasts are critical. If a particle is super dense, it will be deposited much earlier than a particle that is less dense. So you obtain something like that in this picture. You have big grains of quartz, and this stuff here in between, that's gold, small particles of gold. In details, how it works, it's basically all connected to the energy of water and density of minerals. If the water has a lot of density, if the stream is powerful, it can carry particles far away. But if you have features like that, you will deposit first the heaviest particles, minerals and metals with the highest density, and then you will have deposition of metals and elements with a lower density. So you have to look at basically traps like that in streams or paleo streams to check if you don't have any placer. You have this kind of feature as well. Basically, they are riffles, and the particles that are carried at the bottom of the stream, so the dense particles, that means gold or platinum, and they are basically trapped by the riffles. And then we can expect to find high concentrations of interesting elements and minerals. Okay, the last type of supergene deposits, mineral deposits, supergene deposits. Two main types. Supergene means near surface process. We are really talking about the surface of Earth. We are talking about no more than a few dozen of meters compared to the other processes we have seen that is very, very shallow. Lateritic weathering is one of the process to form supergene deposits. That's the concentration of minerals due to the gradual chemical and physical breakdown of rocks in response to exposure or at or near the Earth's surface. And that's the way you form bauxite, which is the main aluminium ore. Basically what happens, you leach everything from the rock, you transform the rock into a soil, you keep leaching all the elements, and what is left behind is iron and aluminium. I talk about that very quickly after. The second the second supergene process is secondary enrichment process. That occurs after the rock was formed. And for example, you have groundwater or stream that goes across a disseminated sulfide deposit. The water dissolves the sulfides, carry with it all the elements that were basically enclosed into the sulfides. And at some point, the physical and chemical conditions changed. That means pressure and temperature, most likely temperature, also physical conditions, also chemical conditions. And then all the elements that were carried, transported by the water precipitate to form a much more concentrated deposit. Okay. Just a word about bauxite. That's the aluminium ore. It looks like that. It's really red because it's full of iron as well. As I said, you start transforming a rock into a soil, and you keep transforming the soil until you leach everything. You transform the clays in the soil into basically aluminum hydroxide. And then you have bauxite, which is that it forms small pellets like that. That makes some Australian dirt roads very dangerous. And sometimes it's consolidated and it forms this kind of rock. So this is how it goes. You have a magmatic rock, in this case, a peridotite, which is magnesium and iron rich. You alter this rock, you form a soil, and then you keep leaching, altering, transforming the soil, and you form an iron oxide layer. It's a crust basically. Underneath, you have nodules of iron oxides. This is the small pellets we have seen previously. And underneath, you have laterites. Basically, you have to remember, start with the rock, you destroy it physically and chemically. You form a soil, you keep destroying it, you leach everything, and at the end, you have iron and aluminium. Okay, just to wrap this up, the demand of for chemical elements and metals in the future. This is a diagram showing what we need in terms of different chemical elements, metals for electric cars compared to conventional cars and power generation. A lot of, what is this color? Graphite or?
Yeah.
Yeah, I'm a bit colorblind, so that's difficult for me. Anyway, what you have to understand, we need a lot of stuff. And this one is also another way to illustrate that. This is the demand. This is the expected, that's the curve of supply. That's the expected supply. And this is what we need. We need a lot. The problem, if we need a lot, that means a lot of mining. And sometimes mining turns ugly. And this is what you see. Okay, that's a big hole. Maybe it's not a big problem. You can fill it with water and make some kind of resort nearby. But if you want to swim in there, that's not a good idea. Usually when you have, for example, mining operations in volcanic massive sulfides or SEDEX, a lot of sulfides. That means you release a lot of sulfur, sulfur combined with water, and you make what? Sulfuric acid. That is Rio Tinto because it's red, because that's the famous Rio Tinto in Spain, from which the mining company took its name. The nice color here is because it's acid, all contaminated. I don't know, that's a very weird color. I expect that is some kind of contamination. Mining operation is not, presents some drawbacks, and like dealing with tailings, dealing with contamination of soils and water, even air sometimes. So if we want more mining, we have to take some steps to avoid disasters, basically. So maybe we can go in space and use space resources for what we need. And that would be it for today. Any questions?